So now we come to a reaction, which reaction was done, and afterwards we read out the data, do the simulation, and make a comparison between the model and the experiment itself. In this case, we look at nucleophilic substitution. It's somehow validation reaction that we are using. We see in blue is the experiment, and in red is the model. The dotted lines are the jacket inlet temperature, and the lines are the bulk liquid temperature. We see in blue the experimental lines. We have a little bit of going up and going down temperature at the beginning, but afterwards we are cooling to roughly 30 degrees for a certain time, and then we go again up on the jacket inlet temperature. We also see the bulk liquid temperature is going up, then we cooling with the jacket, then temperature in the bulk goes down. Again, then when we rise our jacket temperature, we go up. On the right side, we see the assumptions which we have done in the model. So we see the jacket inlet temperature control at this time. We have the controller values. We have stirrer speed, 147 RPM. We have the reaction enthalpy, which was measured on an RC1. It was about minus 141 kilojoule per mole. We assumed first order kinetics, a dosing rate of 4.2 liter per minute, and we made the calculation with density, heat capacity, conduction coefficient, viscosity of the pure solvent. And we were very accurate in the prediction of the temperature itself. Then we had another so-called validation reaction, the deprotonation reaction. This was interesting because we see now afterwards that the dosing was changed due to the rising temperature. Again, we have in red, we have the model, and in blue, we have the experiment. The lines are the bulk liquid temperatures, and the dotted lines are the jacket inlet temperatures. So we see, and the black line is the dosing rate. So we see we start at inlet temperature of about 2 degrees, and then with a dosing of 4 liter per minute. And we cool down to about minus 70 degrees. And as reaction goes on, we see temperature rises up to 10 degrees. Afterwards, the dosing was reduced to a very small amount, about 0.5 liter per minute. And then afterwards, an inlet, when the jacket inlet temperature has about minus 16 degrees, and the bulk liquid temperature has come down to again 2 degrees, we again open the dosing to the amount of 3.5 liter per minute. On the right side, we see the assumption. We measured reaction enthalpy of minus 75 kilojoule per mole. First order kinetics was assumed, and plus minus 1.9 degrees difference. I must also say that for this reaction, the first order kinetics assumption was not so accurate. But again, we see we could predict very well the temperature progression as function of the dosing. So for this is a very nice example for how the model could be used. Then I have another example. This is a distillation rate prediction for a technical scale-up. We had a reaction where we had a reactant A plus B gives a product, methanol, but we have some boundary conditions we have to take into account for this distillation. Reactant A is dissolved in DHF toluene, and we do an azeotropic distillation of the formed methanol so that the reaction can run to completion. We are dosing reactant B and toluene within 4 to 7 hours at a constant reaction volume. The temperature range has to be between 20 and 30 degrees during the distillation. And one of the reasons is that high THF concentration. One of the reasons why we are doing this distillation is that high THF concentration slow down the reaction, and low THF concentration would cause a drop out of the product itself. So there was the question, somehow a simple question, but not so easy to answer. What pressure and jacket temperature for a 40-liter reactor will be used, and what is the distillation rate of this process? So the question, we try to answer the question in a way that we looked only at the solvents. So somehow to predict the methanol which is formed with the reaction, we combined it with the toluene which we are dosing. On the right side you see the picture how the model is set up. So we have a model where we do the distillation, we are heating it. The vessel was measured, so we had a UA value of about 80 watts per Kelvin. We also have a mass transfer coefficient of 0.1 seconds, and the settling time of 3 seconds. Jacket temperature was set 30 degrees. We do also the phase equilibrium calculations, and the heat of evaporation was calculated with that of the pure solvents. If you look now on the graph itself, we see the temperature levels of between 20 and 30 degrees could only be held during the distillation itself when we do pressure steps. So in the first hour, we were about 70 millibars, then we go down to 60 millibars, and in the end we were about 45 millibars. And you see the prediction and the real measured values of the temperature itself was very accurate, but also the distillation rate was very good. You see the dots is the distillation rate in kilograms, which were measured during the distillation itself, and the line is the model itself. So this was one experiment to check the calculations, and it was really, I was surprised how accurate the prediction was. But then we had to do the scale up on a 4,000 liter reactor. Again, the question here was for the market production, what jacket temperature will be needed for 4,000 liter reactor, and what will be the distillation rate? Here we had the problem that the reactor was not characterized. So what is the heat transfer coefficient we're going to use here? We could have done on a very simple calculation, but in the end we decided to do it with a distillation test. So again, we had the same model like before, and we fitted our results to the model, and so we extracted the heat transfer coefficient of about a UA value of about 4,500 watts per Kelvin. You see here the blue line, the pressure was about 100 millibars in the beginning, and we had a very good condensate rate, and also the temperature was about 40 degrees. So this was not the ideal process. This was only for having data for the UA value. After that, we do again the calculations in the model, and we came out with ideal process parameters. The jacket temperature was 40 degrees, and distillation rate was 400 liters per hour at a pressure of about 40 to 60 millibar for a reaction temperature of 25 to 30 degrees. The condenser was also in this calculation. The condenser was an important item because we have seen that in the first calculation the condenser was too small, the one that is used in market production. So we had to exchange also the condensator with the values we had in the simulation of this 400 liter per hour. So this was a very nice prediction of the distillation rate, where you used the heat transfer coefficient of the reactor, but also the values of the ternary mixture.